Hello, welcome to today's LeetCode problem. We're going to walk through this problem that showed up in a contest. Determine if a cell is reachable at a given time. I'll recap the problem description really quickly. We're given a starting index at coordinates sx, sy, and destination coordinates fx, fy. We also have a non-negative integer t that represents the number of seconds we have to reach the destination from the starting point. We can move to any directly adjacent cell from our current location, including diagonally adjacent cells, in 1 second, and we can also revisit cells that we've already been to. Our task is to output whether we can reach the destination in exactly t seconds. Now, this problem looks a lot like a classic recursion or DP problem, especially given the low acceptance rate down here. But there are a couple of hints in the problem description that indicate that that's not the way to go. The first hint should be that in a DP problem, you typically want to create some initial array in which you'd populate the results of your subproblems. But how big should your array be in this case? Well, you're told that the grid is infinite, and the constraints that they give you here are that each coordinate can be 1 to a billion. So you would have to initialize an array of size 1 billion times 1 billion, which is insane. A single integer is 1 byte. So an array of size 1 billion squared would be 1 billion gigabytes, or 1 million terabytes. Needless to say, your computer probably doesn't support that. So that's the first sign that this might not be a DP problem. The second hint is that the problem actually says that you can visit the same cell multiple times. So let's digest that for a second. Let's say that t equals to 10, and we've reached the target at t equals 8. Well, what can we do from here? Well, we can actually just step to any adjacent cell at t equals 9, and then return to the finish line at t prime equals 10. And then, if t were equal to 12 instead, then we can just continue doing the same thing. We can just step back to some other random cell and set at t prime equals 11, and then go back to the finish line at t prime equals to 12. So if t minus the current time is an even number, so if t minus t prime is equal to even number, then we can just return true immediately. But wait, it actually gets even better than that. Let's say, once again, that t is equal to 12 seconds, and let's say that t prime this time is not equal to 8, but to 7. Let's say it's equal to 7. So now the difference between t and t prime is an odd number. Well, can you still reach the finish line in exactly 12 seconds? Well, it turns out you can. Instead of stepping to just one cell, we can step to first one cell, and then instead of immediately returning back to the finish line, we take one extra step. T prime equals to 9, return at t prime equals to 10, and then once again, take another step to the right, t prime equals to 11, and then go back to the finish line at t prime equals to 12. So even when t minus t prime is equal to an odd number, we can actually still return true. Also note that as long as the starting point and the target cell are different, we'll never encounter a case in which we end up on the target cell with t minus current time equals to 1. The reason is that we can always take an extra step before reaching the target cell. Let's walk through an example of that. So let's erase all of this. And let's say that, that we are at the finish line at t prime equals to, at t minus t prime equals to 1. So let's perhaps say that t was equal to 10, and let's say perhaps that t prime equals to 9. Well, how would we end up in that case? The only way we could end up in this case is if we were at an adjacent cell at t prime equals to 8. But it turns out, because this grid is infinite and we can visit cells like any number of times, we can revisit the same cell multiple times. Instead of moving from here, t equals 8 to t prime equals to 9, we can first move to an adjacent cell at t prime equals to 9, and then reach the finish line at t prime equals to 10. So there's basically never a case in which you are forced to land on a finish line exactly one time unit before the target time unit, unless the start and the finish are the same. So if that's the case, when would we ever return false? There's actually two cases for this. So one case is when the distance between the start and finish, is actually greater than the time limit that you're allotted. So the first case is in which t is less than the distance. The second case is that one that I mentioned earlier, which is when the start is equal to the end. So start is equal to the finish, and t is equal to 1. Right? Because if you start on the finish line and you only have 1 second to move, you're going to be forced to move away from the finish line in that 1 second that you have. For the case in which the start and destination are the same, we can just hardcode that case in. For the case in which the time limit is insufficient to reach the target cell, we need to determine what is the minimum distance from the start to the finish. As long as the minimum distance in units of cells is less than or equal to t, we know that we should return true, because we can always take extra steps around the target and stall time infinitely if we get there early. So what is the minimum distance? Well, let's take a look. Let's first erase what we have already so we don't clutter up our board. So the minimum distance is always going to be a diagonal followed by a straight line to the finish. So if dx is going to be our difference in horizontal units and dy is going to be our difference in vertical units, then the length of the diagonal is always going to be the min of dx dy. After traversing the diagonal, we still have max dx dy units, dx dy, minus min dx dy units to traverse. Adding these two distances together, we end up with min dx dy plus max dx dy minus min dx dy, which ends up becoming max dx dy. This seems kind of counterintuitive, but hey, math is math. So since max dx dy is equal to the length of the shortest path between the start and finish, we just need to check that this length is less than or equal to t. And we'll have our result. Let's give it a shot. So let's first hardcode that first case where the start and end are the same and we have 1 second. And next, let's just say that if max dx dy is less than or equal to t, return true. Now let's go ahead and run this and sanity check that it works. And finally, let's go ahead and submit this. Cool. And now if you really want to flex on your friends who really tried a complicated DP solution, you can even do this in 1 line. Yep, and that's how you do this problem in 1 line and in O of 1 time. I'll see you in the next video.